Welcome back to the next session where we begin to analyze specific forms of severe weather. So I hope you're hanging onto your hat and as we go into a very violent aspect of meteorology. Uh, we first are going to look at the difference between a severe weather watch and a severe weather warning. I want you to make sure you have those two straightened out so you know which is which. Uh, we will spend a little bit of time speaking about wind shear, two kinds of wind shear, velocity and directional shear. And then we will go into several different kinds of severe storms. And this is the first of two sessions, actually, on severe weather analysis. We'll finish up next time looking at derechos and flash flooding. So, first of all, a severe weather watch is issued by the Storm Prediction Center in Norman, Oklahoma. They have teams of meteorologists who are looking constantly out for severe weather. And when they see the potential for severe weather, they issue a watch. Watch is for a large area, which means that the potential exists for severe thunderstorms. Maybe nothing is happening at the time, but the potential exists. And by severe weather, we mean winds in excess of 50 knots, large hail, dangerous lightning, or torrential rain. So this is a severe thunderstorm watch. We will talk about tornado watches in a couple of sessions when we look at tornadoes specifically. A warning is issued by the local weather forecast office. In our case, that's at Sterling, Virginia, just north of Dulles Airport. And they have responsibility for Delaware, most of Maryland, and most of Virginia, DC, of course. And a warning is a much smaller area. Severe weather warning, for instance, could be part of Montgomery County. And it means that severe weather is imminent or indeed spotted by either Doppler radar or a certified spotter. I'm one of those spotters, and I have a code name that I call in if I see something that should be noted by the forecast office as being severe weather. And so the Skywarn spotter network is really essential to the issuance of warnings, all kinds of severe weather warnings. So watches are for a large area, potential exists. Severe thunderstorm warnings are for a very small area and warns us that the severe weather is imminent or actually in progress. Let's look at something called wind shear. Any sudden change in wind speed and or direction with height. So there are two kinds of wind shear. Velocity shear, in this case we're looking at a sounding from Birmingham, Alabama, during a time when the atmosphere was very unstable. The surface wind is only at about 5 knots. But if we go up to about 5,700 meters, we find out that the wind is howling at 60 knots. This is called velocity shear because there is a sudden, drastic increase in wind speed as we go up in height. And so that's velocity shear. Directional shear is something a little bit different. If we look at the surface here at BMX, we notice that the wind is coming from the southeast. From the southeast, remember, We don't care where the wind is going. We only care where the wind is coming from. And so the wind is coming from the southeast, but at 500 millibars, if we go up to 500, we find out that the wind is coming from the southwest. That's nearly at right angles to the surface wind. That's directional shear. And what we would notice if we looked at the clouds on a day like this is that maybe there are two layers of clouds going in not opposite directions, but at right angles to each other. That's directional shear. Both kinds of shear indicate that there is potential for dangerous weather. So let's look at the first kind of severe weather. This is called a multi-cell thunderstorm. In this case, we are looking at probably 4 or 5 different cells in a line. The line goes from southwest to northeast. The storms on the northeast end are dying. The downdraft is dominating and they are dying out. On the southwest end of the line, the storms are growing. And this is because the moisture feed coming from the southwest is moving moisture into those new storms and depriving moisture from the storms that are dissipating. And so storms go up on one end and go down on the other, multi-cell thunderstorms. An extremely long line of multi-cell storms is called a squall line. In this case, we have a radar image of a squall line crossing Kansas, Oklahoma, and Texas. And you see the oranges and reds indicating very strong updraft, very heavy precipitation. The reds are probably hail. Notice also that there are at least 2 areas in this squall line that are bowed out. These are called bow echoes. And bow echoes indicate extremely fast straight line winds, not necessarily tornadoes. These are straight line winds that can do a lot of damage. And so meteorologists look for these bow echoes in a squall line that may go for hundreds of miles. Here is a cluster of thunderstorms. This is called a mesoscale convective system. These mesoscale systems can get extremely large, as you can see from the outline of the state of Iowa, that this MCS covers almost the entire state of Iowa. Now, I would suggest that you watch the video that goes with this on the next slide. In fact, all the videos in this presentation, we will take a look at most of them during our discussion session after this lecture. We won't take the time to do it during the lecture itself. But MCSs are interesting because they happen at quite a different time of day than most severe weather. So there's a low-level jet that feeds moisture in from a moisture source. It happens usually in the middle of the night. Why? Because in the middle of the night, the boundary layer, the layer of the troposphere that's closest to the ground, decouples. Remember that from local weather? It decouples, it cools. And so the storm actually rides on top of this decoupled surface, which is nearly a frictionless surface to ride on. And that means that the storm does not lose its power due to friction. This happens also mostly in the Great Plains. As you go from east to west or from south to north, the topography slopes gently upwards, and of course that will cause a form of Rechecke that assists in these storms getting so strong. So these are in the middle of the night. They can cause flash floodings. There can be weak tornadoes. And I have seen, during my time in Kansas, I have seen MCSs or MCCs, as they're called also, I've seen them produce just nearly a constant display of very strong cloud-to-cloud and cloud-to-ground lightning. Let's look at the supercell in detail. A supercell thunderstorm is quite different from a normal thunderstorm. Notice how the thunderstorm tilts. It's tilting because the wind at upper levels is very fast, causing a jet stream. And this causes this thunderstorm cell to become abnormally strong. As you can see with the cross section here, a lot of the precipitation is falling out of the cloud, in front of the cloud, where it evaporates. And evaporation is a heat absorbing process, and that cools the air, and cool air sinks, becoming a very strong downdraft. Notice also the overshooting top. The overshooting top actually presses the top of the thunderstorm up into the lower stratosphere. Why? Because it's kind of like sitting on a beach ball in a swimming pool. If you sit on it and then let it go, it pops up out of the water momentarily, leaving the water. And that's what's really happening here, is a very strong updraft pops up into the lower stratosphere above the tropopause. These storms can rotate. If there is directional shear in the area, they rotate. So let's go through this again. Forward tilt, strongly rain-cooled air, overshooting top, rotation, cyclonic, counterclockwise rotation. The dangers of supercells are many and varied. Microbursts, strong tornadoes come out of supercells, the strongest ones, and large hail. So here are some images of supercells. Notice the very large anvil top to this cumulonimbus cloud. Here's a supercell picture that was taken by a passenger on board a commercial aircraft coming in for a landing at Reagan National Airport. This was, I believe, in 2001, maybe 2002, I can't remember. This supercell spawned an EF5 tornado, which hit La Plata, Maryland. And you can see clearly the overshooting top. Can you see the rotation? It's pretty easy to see the rotation in this Kentucky supercell, as it is in this one too. Rotating supercells are by nature very, very dangerous. A particular form of supercell is the microburst. And again, we will show this video during our discussion session after the lecture. But here is how a microburst forms. Precipitation begins to form. It falls into a dry layer midway down in the atmosphere. And almost all of the rain or Bergeron snow, all of it evaporates or sublimates. And evaporation and sublimation, as you now know, are heat-absorbing processes. They are taking heat away from the environment and causing the air to be extremely cold. And extremely cold air is extremely dense, and that air begins to fall rapidly. It's channeled down into a downburst that comes all the way to the ground. And so it drops rapidly, reaches the ground, and goes out in both, or in really all directions at high speed. How high is the speed? Could be up to 100 miles an hour, and that does a great deal of damage. Microbursts are particularly dangerous, though, for landing aircraft. Take a look at this diagram. An aircraft coming in for a landing at the airport runway. Aircraft typically come in against the wind. And so if the pilot does not know that there is a microburst in progress, he or she will come in against the wind, come under the downburst or the downdraft, and then all of a sudden discover that the airplane is flying with the wind and with a very strong wind. And what that does is that lowers the nose of the aircraft, lowers the altitude of the aircraft suddenly, and what results tragically is that often the aircraft crashes before the runway. This happened with alarming frequency before the FAA, Federal Aviation Administration, put into effect a Doppler radar system. This is different from the National Weather Service Doppler radar system, or the one you may see on your local TV. These Doppler radars are operated by the FAA for the specific purpose of finding microbursts. And since that Doppler radar system has gone into effect, there have been very few accidents resulting from aircraft trying to land under a microburst, thankfully. There are such things called dry microbursts or heat bursts. This happens when the atmosphere is so dry on the way down that not one drop of rain reaches the ground. Up until the time of Doppler radar, no one had really confirmed the existence of dry microbursts. But here's one in progress, and we will watch the video of this heat burst. What happens is illustrated in this very detailed meteogram. This is from Wichita, Kansas in 2011. And so let's look at the details of this meteogram. First of all, the wind shifts. It shifts suddenly. Of course, that can be dangerous to pilots. We've already looked at that. The wind gusts. But look at what happens to the temperature. The temperature goes from the 80s up to over 100 degrees, and the dew point drops all the way down into the 20s. So the air becomes extremely hot and extremely dry. This is a danger to livestock. And before the advent of radar, uh, ranchers were complaining to the Weather Service, why am I losing livestock to heat stroke during these events that nobody really had documented? But since the advent of Doppler radar, we do know now that heat bursts do happen. Well, this is ominous, a roll cloud. Actually, not as ominous as you think. A supercell is in progress. The downdraft is producing a gust front, an outflow boundary, if you will, out in front of the thunderstorm, a mesoscale cold front, and that outflow boundary is moving into unstable air. And so this line is not the thunderstorm. It's in advance of the thunderstorm, but it certainly should be taken seriously because it indicates that right after this, that this area will experience a severe thunderstorm. And then finally, this is a wall cloud. Now, a wall cloud is a step in the direction of a tornado. This wall cloud has dropped down to nearly the surface, as you can see. What you can't see necessarily is that this wall cloud is rotating rapidly. It is the bottom part of what is called a mesocyclone. And we will take a look at mesocyclones in a couple of sessions when we look at the anatomy of tornadoes. So this brings us right to the end of part 1 of severe weather analysis. As I said, we will cover derechos and flash flooding next time. But now you will have an analysis question sheet to fill out, and basically you can use either this lecture or you can use the PowerPoint slides that I've posted already on Blackboard to answer these and turn them in. And so this ends this portion of the lecture. We'll see you next time.